So after this beautiful lecture and this great discussion, you will now get purely experimental talk. So it will be about facts. You probably realized that in my title, the word existence or non-existence is missing. And I say known and missing particles, just on purpose. Okay. So I would like to touch a few points which are related to particle physics. Namely, let's start with two infinities, so particle physics versus cosmology and astrophysics. Then I would say a few words about standard model of particle physics and the fundamental particles of matter and their interactions. Then I would say a few words about Higgs boson, why it took so long to find it, what is the present situation, then a little bit about the neutrinos, which are the most puzzling particles of the standard model, and I will touch a little bit the experimental situation in searches for dark matter candidates. So two infinities, I think both cosmology and astrophysics and particle physics, on the other hand, try to answer the basic question, what has happened immediately after the Big Bang? But we apply a different methodology to do that, to answer those questions. So there is the scale which shows, you know, on one hand is 10 to 28 centimeters of the present situation, and the other end is 10 to minus 32, so just a Big Bang situation. It happens that, let's say, us and what surrounds us is somewhere in the middle of the scale. So I put Copernicus here because it's the conference organized by the Copernicus Center. And so astronomy, astrophysics, so experiments there try to touch this very end. So try to look as far as possible in space in order to answer the question, what happened after the Big Bang? While particle physicists try to reproduce particles which existed immediately after the Big Bang, and this way to answer the questions, what has happened then. And so if you look at those different scales, so what we are able to get now with the highest energy accelerator we have, it's 10 to minus 16. So if you just look at atoms, then it's 10 to minus 8, around 10 to minus 8 when we rounded the proton dimension is less than 10 to minus 12. So 10 to minus 16, this is what we are able to do now, using in the experiments at the accelerators. So, as I said, we have different methodology. Now, LHC is the most powerful accelerator nowadays, which is working at CERN. It started with taking data at 7 tera-electronovolts. Electronovolts is the unit of energy which particle physicists love. So it's the energy which acquired particle with a charge, of electron charge, when it passes the difference of voltage of 1 volt. So, so tera-electronovolts are just the highest energies which are obtained from the accelerator nowadays. And so LHC really entered us to the new energy, allowed us to study particles at the new energy frontier. And now just a few pictures from construction of the accelerator. And now concerning the methodology. So LHC is just the last accelerator in a chain. One cannot accelerate particles from the very beginning up to this highest energy. So it must be done through a series of accelerators which are optimized for different energy ranges to really reach this highest possible energy. So at CERN, as you see, there are several accelerators. So their role is, as I said, they are intermediate accelerators for this highest energy achieved in the LHC, but they also have very interesting their own programs. This I will not touch this point, but however, we should remember that there are extremely interesting things which are being done at lower energies also. So some, again, a bit about methodology of particle physics. So we accelerate for particle physics studies, we accelerate stable particles. Up to now, there are protons, antiprotons, electrons, positrons, and heavy ions, stable isotopes. But also, there is a quite interesting branch of nuclear physics when radioactive ions are accelerated, but this is in the low energy range. And there are very interesting results, by the way. But now I limit myself to particle physics. And then, so in principle, we are doing physics now with colliders. And so you can, the accelerators which really somehow help us to make progress in particle physics were proton-proton colliders, proton-antiproton colliders, and electron-positron colliders. Usually, so if proton-proton colliders are used to access higher energies, but collisions, but in this case, we are colliding composed objects. So because protons are built up of quarks and gluons, so there is extremely difficult situation from the experimental point of view when one analyzes those collisions. Why, in case of electron-positron colliders, we are accelerating fundamental objects. So the situation is very clean, it's very nice to interpret, easy to interpret from the experimental point of view. But electrons are light particles, and unfortunately, we are limited by synchrotron radiation for circular colliders, so one should think for future about linear colliders or very large radius circular collider. So, but here I showed this picture which illustrates, it comes from the lab collider, and it illustrates how precisely with small errors and so on one can really study production of particles in E plus E minus collisions. So that's about the part of the methodology. Apart from accelerators, we have to have detectors. And now the largest, very complicated detectors are presented here. There are detectors which are now for the experiment at the LHC for the 4 largest experiments. And here, just for example, the Atlas detector, it's a very modern instrument, which is 20 meters high, 40 meters long. So you can imagine, this huge building full of electronics. And so some people like to say that they are modern cathedrals. Personally, I prefer those medieval cathedrals, but certainly these instruments are great. So just to show you, those small pieces of equipment during the construction of the detectors. So it was then transported to the tunnel underground. So standard model of particle physics, which are the fundamental particles of matters and their interactions. So just to remind you, so we have matter particles, which are fermions. We have quarks, which are quarks with charge plus 2/3 and quarks with charge minus 1/3. We have leptons, which are charged leptons and neutral leptons, which are called neutrinos. And we have particles which mediate the interactions. So Z and W bosons for weak interactions, gluons for strong interactions, photon for electromagnetic interactions. And standard model has been tested over decades with high precision. However, one critical question left open for quite a long time, namely the question, how do elementary particles acquire mass? And this question was opened only recently, only a few years ago, at the LHC. So one comment concerning this picture of, as we say, free generations. So this is a purely experimental fact that there are free generations. There's very precise measurement which was performed at the LEP collider, so predecessor of LHC, which was E plus E minus collider, when the shape of the Z boson was very precisely measured, and the measurement of the so-called related to the number of the contribution to the width and cross sections coming from neutrinos was measured, and it was clearly visible that the experimental data correspond to free neutrino pairs. So it means that if only neutrinos are less massive than half mass of Z0, which is huge value as compared to what we know about neutrino masses, so it's a very safe assumption, it means that there are only free generations. Why free generations? This we don't know. This is one of those inconsistencies about which Christopher was talking before. Now, what is also interesting, for a long time, astrophysical measurements allowed for the fourth species of neutrinos, which means allowed for the fourth generations. And now the recent measurements from the Planck experiment and sky surveys are consistent also with free. So there is a consistency now. So a few words about Higgs boson. Higgs boson, why it took so long to find it? The simple question is because Higgs boson is heavy and is very rarely produced. So one had to wait a little bit to develop proper experimental apparatus, which means this proper accelerator and then also proper detectors. And once it was found at CERN in 2012 in two experiments, EMS and ATLAS, then the Nobel Prize in Physics in 2013 was given to theorists who invented this mechanism of mass, of giving mass to fundamental particles. So LHC started to take data in the year 2010. There was 2 years of pause when the energy was upgraded to 13 TeV. Before this pause, data was taken at 7, and 8 TeV. Now the data is taken and 2000 at 13 TeV. And it was, so you can see, so 2011, then at this lower energy, and then a lot of progress. And then in 2012, it was really a big amount of data was taken, so it allowed for the Higgs discovery. And then at higher energy, the data started to be taken in 2015. Then there was a fantastic year, 2016, and this year there are some problems with the accelerators which are not fully identified. So there is a bit worse, but the hope is that during the shutdown it will be repaired, find out. Now, as you see, the experimental situation is not easy. Sometimes the events look like that. Now, on average, there are 30 vertices per single crossing of two beams, which means that from the experimental, in order to find this one interesting event, when we have the production of two muons, so we can identify the Z boson. So this is interesting from the analysis point of view. But this should be distinguished from all those uninteresting vertices. And this is what I said. So protons are composed objects. So there is a very high cross section. So the probability for the interactions is high. So this is really difficult. So and one should look for Higgs boson in such a mess. So one can ask, is it necessary? The answer is unfortunately yes, because if one looks at the total cross sections for collisions of two protons and the Higgs production, cross section of the Higgs boson, there are more than 10 orders of magnitude difference between those cross sections. So it means that one Higgs event has to be selected out of 10 billions of ordinary proton-proton events. So it's also what it means that one should to suppress this enormous flow of uninteresting events in order to find out Higgses. So from this point of view, from the point of view of technology, LHC experiments are really one probably of the most modern experiments performed in the world, because first one has to make the reduction of data and not send them to, let's say, far away from detector, but to do it by the electronics which is settled at the detector, because there is no time. Just the collisions are every 25 nanoseconds. What does it mean? It means that particles producing the collision in one crossing of a beam, of two beams, go away by 7.5 meters when the next collision happens. So in principle, at the same time in the detector, we have always two collisions, one from a beam. So it's really extremely demanding from the experimental point of view. And this works. So Higgs boson decays on many different ways. A relatively clean decay channels is Higgs, which decays into two photons. Also, clean channels are looking for events when there are 4 leptons in the final states. And this was clear to all the experimentalists, when one should start from those relatively easy channels and only then at other channels. And what was shown at this famous seminar, Higgs seminar at CERN in 2012, it was, for example, from CMS experiment, this is the signal, which is on a huge background. So one really has to understand background. So this is part of the methodology, distinguish between signal and background, so be able to really draw the conclusions. And now if we look what happened later on, after this announcement of the discovery of the Higgs boson, so the Higgs boson is studied better and better and more precisely. And so it's clear that it's consistent with the standard boson Higgs, more and more. And so it has been zero. There is also a feature which is important, that decay probability increases with masses of decay products, as one expects. And there is also the first result, which was published by both ATLAS and CMS experiments together. And this is still the best Higgs mass measurement, although nowadays the individual experiments, so both ATLAS and CMS, are approaching this precision. So, and after some time, probably again after completing the present run, they will again publish a common result. So anyway, so Higgs, I think, is well established from the experimental point of view. Now it's worth to realize that fundamental particles of matters are fermion of a spin 1/2. Fundamental particles mediating in the interactions are boson with a spin 1, while Higgs boson is a scalar particle with a spin 0. And this is the first fundamental particle of this type. And the Higgs field is everywhere in the universe. So the question is, does this have deeper consequences? Maybe yes. And so it's worth to think about that. Now, in big accelerator centers, physicists start to think what to do later on, when still the current experimental program is in full speed. So the question is what to do at CERN in the future. And there are two concepts which are now considered, and there are studies which are being done, that maybe next step should be a much larger hadron collider to go higher in energy. So this is the LHC ring. It is 27 kilometers of this ring. Why the idea is that maybe one should think about next generation proton-proton collider, which will have the ring length between 80 to 100 kilometers, and with electron-positron collider as a first step. And a very similar idea is now developed in China. So there is, also a competition here. An alternative idea is to have the linear E plus E minus collider, and which is shown here. So again, this is LHC, this is this linear collider. And now there is an idea with different technology, accelerator technology, but also the idea of linear collider has been developed in Japan since quite a long time. And Japanese should say, let's say, give a final answer, yes or no, next year. So in 2018, when the European strategy will be, in particle physics, will be updated. So that's the situation, let's say, with the standard model, which describes the collider data extremely well, with very high precision. It starts to be annoying how well the standard model describes the accelerator data. But we know that this is only the model, which is very incomplete, because it describes only 5% of the composition of the universe, the so-called baryonic matter of the universe, which is around 5%. So more than 90% requires theory which goes beyond the standard model. And as you know very well, so more than 20% this is the so-called dark matter, more than 70% is the so-called dark energy. So, and this requires to get answers. So the questions, fundamental open questions are then, what is the dark mass? What is the dark energy? And what is the origin of the observed dominance of matter over antimatter in the modern universe? And particle physics tries to help to answer these questions related to physics beyond the standard models, just to look for solutions. And I will start with neutrinos, because quite many theorists consider the observation of the neutrino oscillations as the first solid experimental fact from beyond the standard model. There are also some which says, there is nothing special. There are very small couplings, okay, but let's treat them as other particles, and it should work. But as I said, quite many think that there is something special with those very small couplings. And I think this is probably just the only particles which got already 2 Nobel Prizes in 21st century. So the first one was for astrophysical observation based on neutrinos, and the Nobel Prize in 2015 was just for discovery of the neutrino oscillations. So here, when I saw the title of Christopher's presentation, Plato versus Aristotle, I thought about neutrinos' origin. Namely, I think this is a nice illustration to this dilemma, idea versus observation. Namely, there was a long-standing puzzle in nuclear beta decays, which were, it was for more than 10 years. That there are several decays, nuclear decays observed when electrons were emitted, and nothing else was visible except electrons and the nucleus after decay. So from the point of view of observation, it was consistent with a two-body decay, but the energy spectra of electrons were continuous. And it was for many decays, it was not a single decay, but it was consistently like that, which was really a puzzle. So the gamma decays and alpha decays had already been known. And then photons have a well-defined energy, alphas have a well-defined energy, and this unfortunate electrons have this continuous spectra. So Niels Bohr even suggested that maybe energy is not conserved in this microcosmos of nuclei. And then came Pauli with his desperate remedy in 2030. Namely, it's a very famous letter of Pauli to the radioactive ladies and gentlemen, which he sent, which says that maybe we can solve this problem. So I have hit upon a desperate remedy to save the exchange theory, because also spin was not was not conserved, not only energy, and the law of conservation of energy, namely the possibility that there could exist in the nuclei electrically neutral particles that I wish to call neutrons, only later they got the name neutrinos, which have spin 1/2 and obey the exclusion principle. And then it was, as you see, it was formulated with this very, in this way, which was somehow related to the philosophy of science at that time. So because Pauli knew that these particles have to interact very weakly because nobody observed them, they have to be neutral, and in addition, the measurements of electron spectra were consistent with the mass 0 of those particles, so they also had to be very, very light. If not with a mass 0. So he said, you know, I have done something very bad today by proposing a particle which cannot be detected. It's something the theorists should never do. Fortunately enough, the neutrinos were discovered, but it took more than 25 years to do that. And now they are source of very interesting observations. But however, at that time, it was really a dilemma, because he proposed something which could have not been observed. So it was this Plato versus Aristotle. And so I thought that it will be additional example. And now we are able to observe, we've been able to observe all three kinds of neutrinos, which we call neutrino flavors. So it's the electron neutrino corresponding to electron, muon neutrino corresponding to muon, and tauon neutrino corresponding to tauon. And they are massless. In the standard model, they are very naturally massless. And we believed that they are massless for quite a long time, because up to now it was not possible to measure their mass. There are attempts, but still the mass is not measured. So within the experimental accuracy, the mass is 0. And they are neutral leptons, so they can interact only weakly, which causes that they are extremely difficult as objects of studies. But on the other hand, because of that, they offered quite interesting possibilities for studies in astrophysics, because of this very, very, very weak interactions. So if we think about methodology for neutrino studies, the methodology could be summarized this way, that we need to select very intense sources of neutrinos, and we have to have huge detectors to be able to observe interactions of neutrinos. And this is how it is done. And here I would like to show you the flux, distribution of fluxes, neutrino fluxes of different kinds, versus the neutrino energy. And at this end, we have the relic neutrinos, which are, of course, extremely interesting. It would be very, very nice to measure them. And at the very end, we have also some cosmogenic, very interesting neutrinos from the point of view of studies in cosmology and astrophysics. Both are extremely interesting. And here we have different other kind of neutrinos, which we can measure on the Earth. So the most abundant and relatively with a reasonable energy are solar neutrinos. They are neutrinos from supernova explosions. They are geoneutrinos and a subgroup of reactor neutrinos, atmospheric neutrinos, accelerator neutrinos. The energy range of reactor neutrinos is similar to solar neutrinos, the energy range of accelerator neutrinos is similar to atmospheric neutrinos. So the present studies of neutrino properties are based on those artificial sources. So reactor neutrinos and accelerator neutrinos, because here we control much better the systematics. So we really can have smaller measurement errors if we use them. And then, once we know the properties of neutrinos, we can apply them, because we understand them, we can apply them to astrophysical studies. So this is now the, let's say, notion in neutrino physics. So neutrino oscillations, discovery of, it was one of the, I think, most important discoveries in particle physics at the end of the last century, beginning of this century. Namely, the fact that neutrino oscillate means that they have mass, at least two of them have mass different from zero. And so neutrinos are born and interact with matter as flavor states. So there are those three flavor states, electron, muon, and tau neutrinos. Why they travel from the source to the detector as a combination of mass states. So they can change from one into other flavor just on the way. And those changes depends on the parameters and experimental conditions, namely how we choose the energy of neutrinos and how we choose the distance between source and the detector. So we have some influence once we know those theoretical parameters. And they've been, so great discoveries happened in 1998, 2002, when all kinds of neutrinos, which were studies showed, pointed to the oscillations, namely it was atmospheric neutrinos in the Super Kamiokande detector, the solar neutrinos in the SNO experiment, and reactor neutrinos in the Kamland experiment, and the two first got the Nobel, there was the Nobel Prize awarded for those two discoveries, just because it answered the question of long-dated puzzles in neutrino physics. I will not discuss that. I will also skip that. I will go immediately to what we know now about those theoretical parameters. Namely, if we consider three neutrino flavors and three neutrino mass states, we have 6 theoretical parameters, namely 3 mixing angles, 2 differences of mass squares, and 1 phase delta Cp. Cp, this is the symmetry, which is the composed of 2 symmetries, namely C, which changes particle into antiparticle, and P, which is the mirror symmetry. So, and those superposition of those 2 symmetries is the Cp symmetry. This is very interesting symmetry because one of the Sakharov conditions to explain the asymmetry between matter and antimatter, which appeared quite shortly after the Big Bang, requires that this symmetry is broken. So, let's say, almost 50 years of experiments looking for breaking of the symmetry in quark sector. But up to now, this, which is observed there, is consistent with the standard model. And so there are some hints that maybe something would be found, but only hints. No real observation, despite this long story of studies. So the hope is that maybe we can see much stronger effects in neutrinos, because also the mixing scheme for neutrinos is very different than for quarks. Namely, in quarks, the mixing is quite small, Why in neutrinos, one of the mixing angles almost maximal or maximal. There is some discrepancy between experiments. The second one is large, and the third one is much smaller than the other two, but it was also measured, so 3 years ago. And the delta and the difference of square masses for so-called atmospheric sectors are of the order of 10 to minus 3. And for solar sector is 7.5 times 10 to minus 5. So it's more than factor 10 difference between those two. And the question is, what is this value of delta Cp? So this is the program of the future oscillation experiments, which should answer this question. Should answer what is the value of delta Cp of the currently running and future. And there is also this question of that we don't know the ordering of mass states for atmospheric gap. Namely, we don't know whether the third state is below those two, which are nicely ordered because this is done with solar neutrinos. And the other situation in those two are below, and the third one is up. This is called normal hierarchy because the contribution of an electron state in the mass states new one is the largest, so somehow it's natural. And here is opposite, so this is called the inverted hierarchy. And then we have also quite a few other questions which can point to physics beyond the standard model, even stronger than in oscillations itself. So I will mention only one experiment because of strong Polish contribution. In this experiment, this is T2K experiment, so Tokaj to Kamioka, but all those long baseline experiments are always it's the same scheme. So there is the accelerator center in which protons are used to produce neutrino beams. Then there is a near detector which measures neutrino beam before oscillations. Then neutrino are sent for a relatively long distance. In this case, it's almost 300 kilometers. And there is the far detector when neutrinos are studied after oscillations. And then one compares what is expected in case of no oscillation by extrapolating neutrino flux to this far detector and comparing what is measured. And this is all long baseline experiment, neutrino oscillation experiment are done this way. So very, let's say, fresh result from T2K is that according to our measurements, we observe very big delta Cp in neutrinos, for neutrinos. Namely, we can exclude at the 95% confidence level the Cp conservation. But sigma is, of course, far from something which could be considered a serious result. Namely, in particle physics, it is assumed that one can say that there is a discovery of 5 sigmas. So there is still quite a long way from 2 sigmas to 5 sigmas. But however, this is very interesting, what was found. Something which, again, one should remember is that those future huge experiments which are now being approved and constructed and so on for the future to find those sigma for CP violation is also the oh, I'm sorry, it's quite long. But something which needs to be found is the proton decay. which is again one of the Sakharov's conditions to understand the difference between this asymmetry between matter and antimatter. Something which is extremely interesting, and there are now experimental attempts to be applied to solve these problems, is a question of very strange pattern for neutrino masses. When you look at quarks, when you look at charged leptons, then for neutrinos, those masses are by several orders of magnitude smaller. And this is really a question mark. And there are some solutions for that, namely, if it happens that the so-called neutrinoless double beta decay is observed, which means that in the final states we have only 2 electrons without those 2 antineutrinos, it would mean that neutrino and antineutrino are identical. So those 2 antineutrinos, one of those antineutrinos is identical with neutrino, so they can annihilate, and the energy spectrum of 2 electrons corresponds to this channel, then it would be of extreme importance, this observation. It will be the Nobel Prize for sure. So there are several experiments which are performed now to observe that. And now something which I mentioned, which I think is quite interesting, is also the observation of these high energy neutrinos, which there is a recent very interesting results, namely in ice cube at there is evidence for the existence of this extremely high energy neutrinos of astrophysical origin was observed. So the question is now to make a much bigger detector, because up to now this is 1 cubic kilometer of instrumented ice. So the idea is to build 10 times bigger detector. And dark matter, what is it? For physicists, the natural answer would be that there are some unknown particles. So there are searches for those new particles. And there are very, very different proposals and theories. And the most popular are the so-called weakly interactive massive particles, like, you know, neutrinos, but massive neutrinos. But massive particles, and so there are 3 ways of studying them, and in neither of 3, up to now, there is nothing was found. So they are not produced at the LHC, they are not observed in the so-called scattering experiments, and in the annihilation experiments, were quite interesting signals of some excesses of antimatter particles, for example, in IMS experiment. But it seems now that it could be explained by astrophysical sources. So the summary. Up to now, the standard model of particle physics gives an excellent description of the collider data, including the highest energies at the LHC. Neutrinos seem to provide first experimental hints for physics beyond the standard model, and tens of running and future experiments designed to search for new phenomena like baryon and lepton number violation, sterile neutrinos, or candidates for dark matter particles are performed. So I think in 10 years we will have probably a completely different picture. There should be some progress. Thank you.